Hello everyone, welcome to this video. My name is Junyao Zhao. I'm a PhD student at Stanford University. Today I'm going to tell you about budget smooth analysis of submodular maximization and the related problems. This is joint work with my advisor Aviad Rubinstein. Let me use a motivating application to explain to you what is submodular maximization. Suppose we are trying to get our friends to vote, but we are so busy, so we only have time to remind K of our friends to vote. So we select K of our friends and remind them to vote. And then they'll remind their friends to vote, and their friends, and so on. This application can be captured by a problem called influence diffusion. The objective of this problem is modeled as a monotone submodular function. For this specific application, monotone means more of your friends you remind, more people will vote in the end. Submodular means the same person cannot vote twice, even if two of their friends remind them. Besides application in social science, submodular function is often used to model valuation function in economics and game theory. Moreover, it has a lot of applications in machine learning, like sensor placement and feature selection. Now let me formally define what is a monotone submodular function. Suppose we are given a set of elements V, which is called ground set, and we have a function f that maps from any subset of V to a non-negative real value. And we let f of I conditional on S denote the marginal value of element I to the subset S. A function is modular if it satisfies a diminishing return property. Namely, for any subsets S and T, where S is a subset of T, the marginal value of I to S is at least the marginal value of I to T. And the function is monotone if for any subsets S and T, where S is a subset of T, the value of S is at most the value of T. The objective of submodular maximization is to choose the optimal subset of K elements in order to maximize F. Sometimes the cardinality constraint K is also called a budget. This problem is solved decades ago. Specifically, there is a greedy algorithm that achieves 1 minus 1 over E approximation of the optimal value. Basically, the greedy algorithm starts from an empty solution X, and it runs in K iterations. In each iteration, it selects the element that has the largest marginal value to the current solution and add the element to the current solution. It turns out greedy algorithm is also optimal because there is a matching hardness result that says it is impossible to beat 1 minus 1 over E using efficient algorithm. More recent research focuses on designing streaming parallel, robust, or faster algorithms that get 1 minus 1 over E of the optimal value. So what about the missing 1 over E? The point is, 1 minus 1 over E is really just a worst case guarantee. In practice, people observe greedy does much better. How much better? The answer probably depends a lot on application or instance. There's a recent paper that shows greedy achieves 80% to 99% approximation for many realistic instances. A nice open problem in this area is why greedy achieves better performance in practice. What makes practical instances easier? And is there an even better algorithm than greedy in practice? There are many previous work that try to answer these questions by modeling beyond worst case modular functions. For example, bounded curvature measures how close a submodular function is to an additive function. Coverage and undirected graphs, these are special cases of submodular functions. Stability assumes if you perturb a submodular function by a little, the optimal solution doesn't change much. Random perturbation is basically adding some noise to submodular functions. Finally, we have a more recent notion called sharpness. However, these proposals they suffer from two kinds of issues. Either they're just a too strong assumption and intractable to verify in practice, or they simply can't beat 1 minus 1 over e approximation. So in summary, we have a lot of great ideas, but we really don't understand what is a nice submodular function. Therefore, we are faced with a beyond the worst case dilemma. On the one hand, we want performance. We want to account for the missing 1 over e, or at least a fraction of it. On the other hand, we want robustness. We want our model to apply widely to practical instances. And we want the modeling assumption to be easy to verify in practice. Our approach to resolve the dilemma is starting from an overlooked object. Recall that the submodular maximization problem has two objects, a submodular function f and a budget constraint k. Instead of modeling beyond worst-case submodular functions, we can also model beyond the worst-case behavior of the much simpler object, the budget. This approach is motivated by both practice and theory, and we will show we can get both performance and robustness. In practice, many applications of submodular maximization have many users with the same objective function but different budgets. For example, in influence maximization, multiple advertisers try to maximize their influence in the same social network, therefore optimize essentially the same submodular function. However, their budgets can easily differ by an order of magnitude because of different business size. In another example of feature selection, machine learning engineers try to select features for the same machine learning model and the same dataset, therefore maximize essentially the same approximately submodular function. However, the number of features they would like to select could easily range from 100 to 1 million because of different computational resources they have. Finally, in practice, verifying beyond worst-case assumptions for budgets is much more tractable than for functions, because we just need to calculate the empirical distribution of the budgets. In theory, all the existing hard instances break under significant perturbation of budget. Specifically, given a hard instance, namely a submodular function f and a budget k, consider the following new instance where the submodular function is still f, but the budget is changed to either 10 times k or k divided by 10. For the new instance, even outputting a random solution would achieve 95% approximation. Therefore, we revisit submodular maximization by considering average case behavior of the budget. Specifically, we are interested in the following questions. First, what's the optimal algorithm given a distribution of budgets? Is greedy still optimal? Second, does average case behavior of the budget allow the optimal algorithm to achieve better than 1 minus 1 over e approximation in expectation? If not, can we prove a stronger hardness result that is robust to any budget distribution? To formally answer these questions, we introduce a framework called budget smoothness analysis. The name is inspired by the celebrated smoothness analysis by Spearman and Tan. Admittedly, the analogy is not perfect because we need a significant perturbation of the budget. Now let me introduce our model, budget smoothness analysis. First, we fix a budget distribution. For example, the budget distribution of 2020 Democrats candidates campaign. Then, the adversary picks a single worst-case submodular function f. Arguably, all the candidates are optimizing roughly the same function, but have very different budgets. For example, they could use their budgets to maximize the influence over the same social network, which I have explained earlier. Then, we sample a random budget from the distribution. Finally, we run the algorithm on the instance given by f and k. Our analysis shows in this model, greedy guarantees that average candidate's campaign was 67% optimal. Let's do this one more time, but a bit more formally. First, we fix the budget distribution D, and then adversary picks a single worst-case modular function f. After that, we sample a random budget k from the distribution D, and run the algorithm on the instance given by f and k. The performance measure of the algorithm is the expectation of the approximation ratio. The expectation is taken over the randomness of the budget distribution. For this model, our analysis shows that greedy guarantees average case candidate campaign was 67% optimal. So this implies that most candidates are doing better than 1 minus 1 over E just by simple Markov argument. Recall our desiderata. Our model makes no assumption on function, and the noisy model is arguably very simple, so it can be widely applied to many different applications, and can also be verified very easily in practice. How about performance? We explained the 4% out of missing 37%, and our model requires large perturbations. This is good, but not enough by itself. There is room for future work. For example, one can combine the budget-smoothed analysis with a model that makes assumptions on functions to get an even better approximation ratio. We are ready to state our main results. First, we prove that in the budget-smoothed analysis model, the greedy algorithm gives optimal approximation factor in expectation for every budget distribution. This result extends to MapReduce and parallel algorithms that are also greedy type algorithms. By optimal, we mean optimal among efficient algorithms, namely polynomial time algorithm assuming p is not equal to np, or the algorithm that uses sub-exponential number of queries in the value oracle model. We find this result quite surprising because greedy algorithm is independent of the budget. In other words, greedy intrinsically adjusts itself to the budget distribution in the optimal way. Second, we derive a simple but non-convex program that computes the optimal approximation ratio in the budget-smoothed analysis model for any budget distribution. We observe better than 1 minus 1 over E approximation by solving this program for many realistic budget distributions. Finally, we prove a robust hardness result that says no budget distribution allows better than 90% approximation. Because of the time limit, I will not show you the proof of any of these results. But if you are interested, you can read the paper or send me an email. Instead, I will show you the numerical simulation for the second result. Our numerical simulation computes optimal approximation factors for various budget distributions by solving a non-convex program. On the left column, you can see different budget distributions we tried. There are some synthetic distributions like uniform distribution, log-scale uniform distributions, and there are also some real-world datasets, like the top 10 ads campaign on Facebook ads and the 2020 Democratic candidate campaigns. On the right column, you can see the worst-case approximation ratios. Here, worst case stands for worst-case modular function. And you can see non-negligible improvement over the baseline 1 minus 1 over E for all these distributions. In hindsight, Budget smoothed analysis alone is probably insufficient to explain all the missing 37%. That said, there's still some room to improve. In comparison, even the original smoothed analysis showed a huge polynomial runtime for the simplex algorithm, but now it is significantly improved. Moreover, here is why I believe budget smoothed analysis is important and should be applied to other budget-constrained problems. Budget smoothed analysis provides a tractable, beyond the worst-case performance test for the worst-case optimal algorithms of budget-constrained optimization problems. It helps us identify the right optimal algorithm. By tractable, I mean the noise model of budget smoothed analysis is reasonably simple. It allows us to analytically solve for the best algorithm. Also, in practice, we can easily verify our assumption of budget distribution by calculating the empirical distribution. Let me give you a few examples. For submodular maximization, we showed that the worst-case optimal greedy algorithm is also optimal in the budget smoothed analysis model. So it passed the performance test. Now I give you a negative example. So this is another recent project in this direction, where we study procurement auction in the large markets. So basically, this is a knapsack problem. So we have a buyer and a bunch of sellers who have values and costs. The only difference is that in this problem, the costs are private, and therefore we need to design a truthful auction for the buyer to give incentives to the sellers and make them report the true costs. For procurement auction problem, coincidentally, the worst-case optimal truthful auction also has 1 minus 1 over E approximation. We proved that this auction is stuck at 1 minus 1 over E for any budgeted distribution. It is not budget smoothed optimal, so it failed the performance test. Instead, we devised a new auction that is budget smoothed optimal, and it passed the performance test. It beats 1 minus 1 over E in expectation for any non-trivial budget distribution. By non-trivial, I mean there has to be at least 2 budgets in the support of the distribution. That's not the end of the story. We further show that our new auction is instance optimal compared with a large and natural class of auctions, including the previous optimal auction. And empirically, we show that our auction outperforms previous optimal auction by a large margin on realistic markets sampled from many natural distributions. This slide shows the simulation results of procurement auction on synthetic markets. On the left column, we have sellers' distribution of costs. So we use Gaussian distribution, uniform distribution, exponential distribution, and Gaussian mixtures. On the right column, we have the approximation ratios of the previous optimal auction and our auction. We can see that the approximation ratio of previous optimal auction is very close to 1 minus 1 over E for all the distributions. And our auction is able to outperform the previous optimal auction by a large margin. So the takeaway is, if you designed a worst-case optimal algorithm for a budget-constrained optimization problem, budget smoothed analysis should immediately be your next test. If your algorithm is budget smoothed optimal, this provides rigorous evidence that your algorithm is probably also good beyond the worst case. If not, there might be better worst-case optimal algorithms that have better performance in practice. And budget smoothed analysis could serve as a heuristic that guides you towards such algorithms. Namely, during your quest for the budget smoothed optimal algorithm, You could find better worst-case optimal algorithm that performs better in practice. This is exactly how we found the better procurement auction. That's all I want to say. Thanks for watching.